Hello everyone. We are starting a free open lecture on Discord. Our lectures are held weekly. If you are simply an audience member and want to ask your question and receive an answer, join our lectures. You can find the link to Discord in our Telegram channel, where you can also find out the schedule for the lectures. Join us. And accordingly, where is our vector r located? Well, r can basically be in it, in this plane, so that this equation matches. No, r is located between x and b. That is, r is the difference between vector x and vector b. This follows from our equation, that is, this is the vector r, as follows in this context. Because r is basically b minus x, that is, it is essentially located here. So, what is the idea? The idea is that we essentially need to find this solution to the approximate system. That is, we need to find the vector x in such a way that this vector r, or rather its length, is essentially minimized. So I just took some arbitrary vector x, ended up here, and this is the vector r. But what will happen if I take the vector x differently? It will perhaps point somewhere just over here. Then my vector r will be like this. And if I take x in such a way that vector x is here, then my vector r will essentially be like this. Basically, if the principle is generally well understood, when I change x, the vector a and x also changes. The only thing that cannot happen to it is that it cannot escape from this space of columns, from this plane. In other words, it cannot be here. But somewhere I change x, and accordingly, x travels along this plane. The vector x travels, and certainly as x changes, the error also changes accordingly. And we need to make this error, or rather the residual, essentially, in other words, basically fundamentally what? We need to make it as small as possible. Based on this, I have a question for you. What should the vector x be like? Where should it be located so that this r is as small as possible? That is, we have this plane. And as I travel along it, I change the vector x, and x travels along this plane. Where should I place this vector ax? In such a way that the residual, which is the distance between vector ax and vector b, while vector b lies outside this plane, is minimized. At the location of the projection of vector b on plane ax, well, yes, but how do we find the projection of vector b on the plane? What will happen? So, what kind of projection will this be? There are different types of projections. Perpendicular? Well, yes, it will be. That is, indeed, it must be a perpendicular. The vector x, which essentially gives us the product x in such a way that this r will be perpendicular, I will call x with a hat. Basically, fundamentally, it must be perpendicular. Accordingly, this vector will be x hat.
Want to become a great programmer? Subscribe to our Telegram channel.
To avoid this, I stopped using arrows, so I wouldn't have to write vector a, arrow, here vector a with a hat, and another arrow at the top. But you remember that x is a vector, and this is a matrix. This vector is simply x, and I denote this one as x with a hat. Accordingly, for the purposes of this discussion and to avoid any confusion, I will denote this distance as r, which will be used consistently throughout the explanation. This vector, as you can see, since x is in this plane, x hat is also clearly in this plane. Accordingly, their difference, this vector, is also in the plane. I chose them very carefully with a hat in such a way that I have a perpendicular here. It makes perfect sense. Exactly. Let's take a look at all of this from the outside and see exactly how it will look. That is, if we look at this picture from the side, then essentially what happens is that this plane will, in essence, turn into a line from a different perspective. Here I have the vector x, and right here, as you can clearly see, I have the vector b. Here is the distance r, or the residual. Yes, I definitely need to make it as small as possible. I have ax with a hat wandering along this line, and I suspect that if it is here, then this r, which I denote as r with a hat, will indeed be the smallest among all possible r. Here is x with a hat. Well, it is clear that this r is greater than this perpendicular. This is even more even more. I will go in this direction too. Here is the perpendicular. The length of this line is indeed greater. This is definitely even greater. This is even greater. That is, in other words, the perpendicular line should ideally provide us with the least error in the context of our calculations. Accordingly, first of all, we now have two tasks. The first is to try to show with formulas, in detail and step by step, that indeed this residual r is actually shorter in length than it appears. We will do this in a comprehensive manner and thoroughly, ensuring that everything is explained in a clear and concise way. The length of any other vector r, that is, the fact that this residual is indeed the smallest. And after we show this, we actually need to somehow compute this x, that is, how we can indeed actually find it. Indeed, somehow, actually. Matrix A is known, we know vector B, and we somehow need to find vector X with a hat. So we have two tasks here. This illustration is crucial because it provides the key explanation for the entire concept of the least squares method. Is it clear to you? Or do I need to repeat what is happening here one more time perhaps? Maybe once more. Again. Because on one hand, this topic is not very complex and intricate, but on the other hand, it is in fact actually a bit confusing. Indeed. Should I explain again what is happening in this drawing, or is it clear to everyone? So, let me go over it one more time to make sure it's completely clear to everyone. We are solving this system of equations. We need to find beta 0 and beta 1 that satisfy this system of equations. But we understand there is no exact solution. So we will look for an approximate solution. How will we search for an approximate solution? We will transition from system 1 to system 2. That is, here we have added residuals. We added them in order to obtain a system of equations that has an exact solution. This system has a precise and exact solution. However, it is important to note that there will be several such solutions available, each potentially differing in minor details. In fact, there are many. We need to find the solutions for beta 0 and beta 1 in such a way that this error is minimized. We want these residuals to be as small as possible. In other words, in order for the line to pass as close as possible to the original points to the original data. To understand what is happening here, we rewrite system 2 in vector form, resulting in this system 4. Now let's take a moment to carefully and thoroughly figure out what exactly is happening here in this particular situation. I multiply matrix A by vector X in a mathematical context. What does this mean? It means that when I multiply matrix A by vector X, the result is a new vector which is derived from the original vector X. Vector X from two-dimensional space transforms from a two-dimensional vector into a three-dimensional vector X, and it lies in plane. This plane is the column space of matrix A, but this follows simply and clearly from mathematical reasoning, from the definition and properties of matrix multiplication with a vector. That is, when I multiply matrix A by vector X, the vector essentially falls into the column space of matrix A. He cannot go anywhere else, only here. That is, indeed, he lies in this plane. In fact, actually, indeed. If this is vector X, then it can only be in this plane. It cannot be outside of this plane. Well, wonderful. Now, if we had the equation x equals b and it had a solution, then this vector b would also lie in this plane, which means that in the context of linear algebra, it is important to note that this implies that there is no exact solution to this system. We have an exact solution to the system. X plus r equals b. This means that the vector b lies exactly outside of this plane. So this is what we have. The vector x lies in the plane, while the vector b lies outside the plane. But as I already mentioned, this system indeed has many solutions depending on which vector r. How are the solution, that is, the vector x and the vector r, essentially related to each other, and in what manner, essentially? I take some specific solution, that is, essentially the vector x, which consists of the values of two numbers v0 and v1, and substitute them here. and I get some vector x, which lies within this plane. This vector is important as it helps us understand the spatial properties of the plane. The vector x corresponds to some specific vector r, which is indeed actually in fact the distance to the vector b. So our task is to find a vector x such that the distance between it and the vector b is minimal. In other words, we need to determine the vector x in such a way that the Euclidean distance between vector x and vector b is minimized. We have clearly and logically concluded from our reasoning that this must be a vector x, which we will specifically and clearly denote as x hat, located here, meaning it is positioned such that this vector r, which is the distance between A and the vector B, is essentially and fundamentally perpendicular. So we have found it. And now we have two tasks. First, we need to, in order to, rigorously and in a rigorous manner, conclusively prove that this distance r hat, which corresponds to the vector x hat, is indeed the smallest. That this vector has the smallest length among all possible vectors r, and indeed in fact actually to find the vector x hat, that is, we know A, we know B, we need to find it. This will be one of the exact solutions to this complex system. System 4 or system 2, both are valid. It is one of many possible solutions. In this case, it will be such that the sum of the squares of these is essentially minimized. Accordingly, we will consider this solution as an approximate solution to this system, which, in essence, fully satisfies us.
Want to become a great programmer? Subscribe to our Telegram channel.